Okay, so that's a whole lot of equations and so on. Now let's start talking about solution modeling, going beyond the solution, the ideal solution. And I'm going to talk about regular solutions. So your zeroth approximation for a solution would be that it's ideal. Your next approximation in many cases would be a regular solution. Many solutions, if they do not deviate too far from ideal solutions, are approximately obey the regular solution equations. Now, when we talked about ideal gases, I said that most gases, unless you go up to very high pressures, are very close to ideality. I mean, it's a very good assumption that the gases that we're dealing with in material science and that are very close to ideal, deviations of less than 0.1% or more. But with ideal solutions, of course, the deviations from ideality can be very large. You can have excess Gibbs energies, which are several times the ideal Gibbs energy of mixing. You can have activity coefficients. I mean, activity coefficient of an ideal solution is 1. Real solutions can easily have activity coefficients of 10 to the minus 2, 10 to the minus 8. You know, you can have immense deviations from ideal behavior. So an ideal is just a limiting case. So, but if we're not too far from ideal behavior, it has been observed that many solutions are approximately obey regular solution behavior. And the idea of a regular solution is kind of the starting point for a lot of the models that are used. The compound energy formalism and everything. And polynomial models and so on are based on the idea, the physical ideas of the regular solution theory. So let's look at a regular solution, and this is in the book on page 48, section 5.5. We have regular solution theory. All right, this is in page 48. So regular solution theory was developed in 1908 by Van Laar, so this is not a new thing. Now we're past the 100th anniversary of it. Okay, a simple regular solution. This is a definition of a regular solution. That the excess Gibbs energy is the product of the mole binary solution. Product of the mole fractions times omega minus eta t, where omega and eta are constants. Omega constants independent of temperature and independent of composition. So that's your integral excess Gibbs energy is then parabolic. That's a parabola. XA is 1 minus XB. That's a parabola. So I drew it over here. If you were to plot, this is a plot of GXS versus composition, mole fraction of P. Okay, so we have up here, we have the excess Gibbs energy. This is the idea. This is your regular solution, XA XB times omega minus eta t. So here we have GXS plotted versus composition, and your GXS looks like this. If you plot this up, this is equal to 0 at both ends, of course. Goes through a maximum at 50%. At the maximum then, GXS at the maximum is 1/2 times 1/2 omega minus eta t, and it peaks out at 50%, and that is a parabola. All right. Now, what are the partial excess properties, which will give us the activity coefficients? So I said if you substitute this into equation 116, this was equation 116. With just the common tangent thing. Mu xs of b is gxs plus 1 minus b, and so on. That's your common tangent. If you substitute this equation for gxs into this equation, which is the common tangent, which we talked about an hour ago, you will end up with these equations for the partial excess chemical potential. So mu xsa is xb squared times the same thing. So these are also parabolas. Mu xsa, this is xb squared times the same constant. Mu xsb is xa squared times the same constant. Okay, so mu xsa will look like this. It'll be xb squared. So when xb is 0, mu xsa is 0. Clearly mu xsa is 0 for pure A. And then this is a parabola. Don't draw it like a parabola, but it is a parabola. And it's finite at the end. In pure B, mu xsa is omega minus eta t, and the mu xsb is a parabola going the other direction. Okay, and they're symmetric, of course, and all three curves meet at the peak here at 50%. So that's what the partial properties will look like for a regular solution. Parabola, all three parabolas for the integral excess and for the partials. Here I've drawn gxs as negative. I've assumed omega minus eta t is negative. But they could also be positive. And then just turn around and get positive deviations. Okay. but it's, the regular solution says that to a first approximation they're parabolic. Clearly then the omega is the enthalpy term and the a to t is the entropy term. Okay, so maybe, if it doesn't bother Virginia, I'll write it over here. I'll say then the excess enthalpy is equal to xa xb times omega, and the excess entropy is equal to xa xb times a. Clearly your partial heat of A is xb squared times omega, etc. And of course the mu excesses that I wrote over here, well, I can write that over here. Mu excess of B is xa squared, and that's RT log gamma of B. And this is RT log gamma of A. Oops. Okay, so that's what a regular solution looks like, and you have the two terms, split it into the enthalpy term and the excess entropy term. And so these are your excess Gibbs energies. If Gxs is negative, the excess Gibbs energies are negative. The excess chemical potentials are negative, and the gammas are less than 1, and you have a negative deviation of the ideality. So, okay, since you'll be doing some of these things, similar things, I started with the integral equation up here for the integral property Gxs, put it into this equation, which is the common tangent equation, to get the partial properties. And I said about an hour ago that when you use this equation, you're using the molar properties, the molar Gibbs energies. Okay, as an exercise, which you can do at home, let's start with this equation for the integral. This is the molar Gxs, this is joules per mole, I'm using a small g. And let's try to calculate mu excess B directly from the definition of the chemical potential of B. So in that case, sorry, we're going to start over here, and I'm going to say mu excess of B is equal to dg excess dNB when Na is constant. That's your definition of your excess chemical potential. Well, chemical potential is dg dN, the excess chemical potential is g excess dN. Okay? So there you should be able now to derive this equation for mu excess B from this equation, but using this definition rather than this equation. But what you got to remember is that the G up here is an uppercase G, so that is the total Gibbs energy in joules, not joules per mole. So this would be D of Na plus Nb G dNb, a partial derivative, when Na is constant. Okay, so we're writing the partial derivative. I should be writing this as partial. So you're taking a partial derivative. You're taking a partial derivative of the total excess Gibbs energy with respect to Nb, keeping Na constant. And where G then is equal to Xa Xb, so Na over Na plus Nb times Nb over Na plus Nb times omega minus a to t is a constant. Okay, so what you've got to do then is you have to, so that's the definition of mu excess B, is the dg dNb. You make your total excess Gibbs energy is the total number of moles times the molar excess Gibbs energy. And now for the molar excess, so that would be G excess. And the molar excess Gibbs energy then is given by this equation, XaXb times omega minus a to t, where Xa is Na over Na plus Nb and Xb is Nb. So you take this equation for Gxs, substitute it into here, do the partial differentiation, keeping Na constant, and you should end up with the same equation. So to have a little practice using this kind of stuff, I recommend you try that. Take you 2 minutes. Alright, continuing on. Several liquid and solid solutions can form approximately to regular solution behavior, particularly if Gxs is small. So that's what I said. This is the next approximation after ideal solutions. And there's examples for alloys, molecular solutions, ionic solutions, and so on. Gases then generally correspond very closely to ideal solution behavior, to regular solution behavior. Okay, so now we're going to a model. Why should this be the case physically in terms of an atomistic model? Why should this be the case? Okay, so we'll start off with if a solution, a regular solution is assumed to be just like a next step up from your ideal solution. So the same sort of assumptions apply to the ideal solution. That is, A and B are very similar, but not exactly the same now. And I'm going to take the first definition. I'm going to assume, to start with, I'm going to assume that SXS is 0. And that is, therefore, the parameter eta is equal to 0 in the omega minus A to T term here. And the term omega, this is the excess entropy term, this is the heat. So we'll assume this is 0. So in other words, the GXS is entirely enthalpic. Okay, so what we're assuming is we're saying then that we have a random mixture. That is delta S equals delta S ideal. Okay, we're assuming that the deviations from ideality are so small that it doesn't affect really the disorder of the system. The system is still, to all intents and purposes, randomly ordered. Okay, and all the deviations from ideality are because of the enthalpy term. Okay, so they're all due to the enthalpy term. Okay, so how do I put this in the book? Okay, suppose that the atoms' electronic structures of A and B are similar, then the distribution will be nearly random, and the configurational entropy will be nearly ideal. So the excess entropy is equal to delta H mixing minus TSX non-configurational. Okay, so we assume a random mix. Oh, okay, maybe I should have. We're assuming a random mixture. Therefore, okay, SXS is equal to SXS. I might as well do this now. Configurational plus excess non-configurational. So the excess configurational entropy is due to the arrangement in space, the disorder in space. Okay, so I'm assuming that SXS configurational equals 0. And I'm going to assume for the moment that SXS non-configurational also equal to 0 for the moment. Okay, SXS configurational is 0 and the non-configurational is 0, so in other words SXS equals 0, so eta equals 0. Just putting this in, when I say that SXS is 0, I'm making two assumptions. I'm assuming there's no configurational excess and there's also no non-configurational excess. So everything has to do with bond energy. The deviations from ideality for the moment have to do with the bond energy. Okay, so the system is randomly mixed. I'm also going to make even more simplifying assumptions that Z is constant. Z is the first nearest neighbor coordination number. That's the number of nearest neighbors around a central atom. We assume that's constant, is not a function of composition, does not equal a function of composition. So as you go from pure A to pure B, the first nearest neighbor coordination number stays the same. Okay. If you're mixing copper and gold liquid, the first nearest neighbor coordination number is around 12, and we assume it's constant independent of the composition. Okay. So how many nearest neighbor bonds are there in 1 mole of solution? Well, there's n naught Z over 2 nearest neighbor bonds, where n naught is Avogadro's number. So the number of atoms is n0, and n Avogadro. Each atom is surrounded by Z nearest neighbors. And if you got n naught Z, you got to divide by 2, because now you've counted every atom as a central atom. Okay, so n naught Z over 2. So n naught Z over 2 is the total number of first nearest neighbor pair bonds in the solution. And we assume that the distribution is random, that is SXS is 0, so we're assuming it's random. Therefore, the probability that a given bond is an AA bond is equal to XA squared. Okay, so I have a solution here of all my atoms lined up, and the distribution is random. The probability of an A being here is XA. The probability of an A being here is XA, so the probability of an AA bond is XA squared, because it's random. The probability of a BB bond is XB squared. The probability of an AB bond is 2XAXB because you could have an AB or it could be BA. And just to check, XA squared plus XA squared plus XB squared plus 2XAXB equals 1. XA plus XB squared, which is 1. All right, so now we're saying then when we're mixing the solution, we're starting with XA moles of A. Well, this is the reaction we're trying to do here is we're having XA moles of A plus XB moles of B produces 1 mole of solution. And that is in fact the delta G, GXS, delta H. This is the reaction we're talking about, the integral mixing reaction. So we start with XA moles of A, XB moles of B, and we form 1 mole of solution. All right, so what is the enthalpy change? Okay, so delta H then will be H of the solution. Do I write this down here? Maybe I'll write it down. Delta H then will be the enthalpy of the solution minus XA times the enthalpy of pure A minus XB times the enthalpy of pure B. Okay, delta H of mixing is the enthalpy of the products, which is a mole of solution, minus the enthalpy of the reactants, which are A and B pure. Okay, let's find out the contribution to this delta H due to the changes in first nearest neighbor pairs. Because in pure A and B, I have in pure A I have AA pairs, in pure B I have BB pairs, and in solution I have all kinds of pairs. Okay, so let's assume how much energy, how much bond energy changes due to the first nearest neighbor changing. Okay, so it's equal to the total number of bonds, which is N naught Z over 2. Okay, now I'm trying to get this H, the enthalpy of the solution. This enthalpy of solution, this first term, is going to be the enthalpy of the first nearest neighbors in the solution. Okay, well now these epsilons, AA, BB, and AB, they're the bond energies. And again, we're assuming that the epsilons are independent of composition and temperature, just like the Z. Okay, so epsilon AA, that's the energy of an AA bond. Epsilon BB is the energy of a B bond, and so on. And this is independent of the composition, from pure A to pure B, and of temperature as well. Okay, so the first nearest neighbor, so the energy of this first term here is the energy of the first nearest neighbor pairs. So first nearest neighbor pairs, that's how many first nearest neighbor pairs you have. That's the probability that it's an AA pair, that's the energy of the AA pair. This is the probability that it's a BB times their energy, probability of the AB pairs times the energy of the AB. So that is the energy of the first nearest neighbor bonds in 1 mole of solution. From that now we have to subtract the energy of the bonds in XA moles of pure A. Okay, so that's the number of bonds in a mole of solution. That's the number of moles of A, XA, and all the bonds are AA bonds. Plus XB times epsilon BB. So, energy of the first nearest neighbor bonds in solution minus the energy of the first nearest bonds in the pure A reactant and in the pure B reactant. If we put these together and collect terms, we end up with this equation, remembering that XA plus XB equals 1. Okay, and you end up with the enthalpy of the first nearest neighbor terms is a constant times XA XB. So you see we're getting into the XA XB term here now, times a constant. Where the constant is the difference, Jesus, another error. Tab, bare neck. Can I, how does this happen? This here clearly should be epsilon AB. Should be epsilon AB. Minus epsilon A plus epsilon BB. So you can play around this with yourself and combine terms. So the constant then is N naught Z times all this. This C1 is this whole thing here, which we've assumed is constant. Now you can see then that this term then depends upon the difference, and this is AB bonds, the difference in the energy of an AB bond and the average energy of the AA and BB bonds. If all the bonds have the same energy, then this term is 0 and the enthalpy is delta H is 0. Suppose the AB bonds are stronger. Stronger bond means more negative energy. In that case, the epsilon AB is more negative than this here, and so this whole term becomes negative. And that gives you a negative contribution to delta H. C1 is negative. if the AB bonds have a more negative energy than the AA and BB bonds. Okay, so what happens then, if the AB bonds are stronger in the solution, this tends to stabilize the solution relative to pure materials, relative to an ideal solution, okay, which gives you a negative contribution to delta H, which gives you a negative contribution to GXS, which makes the Gibbs energy more negative, and so the solution becomes more stable. Okay, so a stabilization because the bond energies are more stable. If epsilon AB is less negative than here, then the AB bonds are weaker than the average AA and BB bonds, and this entire term becomes positive. Gives you a positive C, a positive delta H, and therefore a positive contribution to GXS. Okay, so weaker bonds, the AB bonds being weaker than the AA and BB bonds renders the solution less stable. The important thing here then is, well, two important things is this term then. We see that the deviations from ideality are depending upon the differences in bond energies, and we see why it should be parabolic. The first approximation, if your mixture is random, your first approximation is going to give you a parabolic GXS, XAXB. So that's just the first nearest neighbor bonds, but you can do exactly the same thing for the second nearest neighbor, third nearest neighbor bonds. Okay, because what's the second nearest neighbor bonds? So the second nearest neighbor bonds, the probability that second nearest neighbors are A and A are still XA squared. Probability that this is an A and the second nearest neighbor is an A is XA squared. The probability of second nearest neighbor BB bonds is XB squared, so on. So you're going to get, if I wrote delta H of second nearest neighbor, I will get exactly the same sort of term, except these would now be the energies of the second nearest neighbor bonds and the third nearest neighbor bonds. So I'm just going to get a whole bunch of terms, C1, C2, C3, and the total parameter omega is then just the sum of. So finally I got delta H of mixing is omega XAXB, where omega is the first nearest neighbor plus the second nearest neighbor plus the third nearest neighbor, and so on contributions.
Sorry, but doesn't the coordination number change with as far like the further you?
Oh yeah, but it's going to be a different Z. It'll be a different Z for second nearest neighbor too. So this will be Z1, Z2, but it's still constant.
Yeah.
Okay, so this delta H second nearest neighbor will be N naught Z, Z2 epsilon second nearest neighbor AB. Okay, so as long as you got a random mixture, and as long as the supposition, I mean, you're making an assumption, of course, that a bond energy has a meaning and that you can add up bond energies, which is not too bad if you're talking about van der Waals or ionic forces, but we're talking about a metallic bond, of course. It becomes a little bit dicey as to exactly what you mean by a bond energy, because the whole thing, but still, what we're trying to do here is rationalize the parabolic nature, which you observe. And this certainly then rationalizes the parabolic nature of it. Okay. I've actually seen the thing derived in terms of only the first nearest neighbors, and it says you're making the assumption that only first nearest neighbor pairs contribute to the delta H. Well, no, all the pairs can contribute, and it all gives you the same the same energy. So there you go. Now there we assumed that that was to give me omega for the heat. Now let us continue to assume that the X, so that will give me a regular solution in which you have a non-zero value for omega and you have a zero value for eta. So the total excess entropy is zero. So it's all enthalpy. And sometimes you will see that defined as a regular solution. By regular solution, someone means the excess entropy is zero. Just to stop confusion, I would call that a strictly regular solution. Okay, so if eta equals 0, then we'll have a strictly regular solution, but this is my own private terminology. Okay, but just when you see somebody says the solution is regular, they can mean two things. They can mean delta H is parabolic and SXS is 0, or they can mean delta H and SXS are not 0, but they're both parabolic. How do we, okay, so this then kind of, this derivation here kind of explains why you should have a parabolic delta H, and the omega is the difference in bond energies. How do we rationalize the SXS being parabolic? That is even a little bit more dicey. So we must assume that the configurational entropy still is 0, and we're assuming that it's all non-configurational. The non-configurational is the vibrational entropy. So we're still assuming now, we're saying where eta does not equal 0, eta does not equal 0, we have regular, but not strictly regular. Okay, for a regular but not strictly regular solution, still, we're assuming in that case that the SXS in a strictly non-regular solution equals SXS non-configurational. That is, we're still assuming that SXS configurational equals 0. So even in a regular solution where eta is not 0, we're assuming that all the excess entropy, in the model anyway, we're assuming that all the excess entropy is non-configurational. So it's difference in the bond, the vibrations of the bonds. Configurationally, it's still randomly mixed, but remember, there's the energy, there's the entropy. As you heat a pure material up, the entropy goes up because of the vibrational spectrum, and we're now assuming that the vibrational spectrum of the solution is not the same as the vibrational spectrum, the phonon spectrum of the pure materials. So now it gets a little more dicey. You can do exactly the same definition as we did before, but instead of talking about an energy of a bond, you can talk about the excess entropy of a bond as sigma AB. So your excess non-configurational entropy is exactly the same equation as here, except these are the differences in the non-configurational entropies of the bonds. And I would know exactly what the non-configurational entropy of a bond is, but let's assume that it's a reasonable sounding term, and so clearly you end up with exactly the same sort of expression for the excess entropy as you do for the heat. And that's kind of observed that way, so. Okay, so simple nonpolar molecular solutions, mixing two nonpolar molecular solutions, mixing carbon tetrachloride with something like that, or simple ionic solutions like molten sodium, molten salts, and so on, exhibit approximately regular behavior. And that, well, to have regular behavior, you've got to have a reasonable assumption that the solution is randomly mixed. And also, it's more likely when your bonds are when the idea of a pair bond and additivity of pair bonds is more reasonable, that you might expect it to be closer to ideality. And I think you kind of observe that. You find regular equation seems to apply more closely to solutions such as ionic salts, simple molecular solutions, than it does to metals. So the assumption of additivity of the energy pair bonds is probably reasonably realistic for van der Waals or colonic forces. For metallic alloys, the concept of a pair bond is at best vague, and metallic solutions tend to exhibit larger deviations from random behavior, both in the heat and even more so in the entropy. I said here, in several solutions it's found that A to T is much less than omega, so the excess entropy term is generally less than the enthalpy term. Okay, so that is the GXS is omega minus XA. So the first approximation, GXS is independent. Again, this is more often the case in non-metallic than in metallic solutions. So even if you find a GXS that's fairly large in a molten salt or a molecular solution, you'll often find that the SXS is quite small. But in metallic solutions, you can find sometimes where the delta H term is not that big, but the TSX term can also be quite large. So metallic solutions tend to have less of a tendency to be regular, or at least not strictly regular for sure. And I think it's basically because the idea of a pair bond is kind of vague. However, the regular solution is, to a first approximation, that's your best bet, that the thing's going to be parabolic. It's not, for most simple solutions, things don't vary tremendously from this kind of parabolic behavior. Now, of course, it isn't always symmetric, it's shifted and so on, but this is your basis for all the polynomial models that we use in CalFAT and everything are all based on basically they're extensions of regular solution theory. The idea that we have a lattice, we have pair bonds, we add them up, and so on. Okay, now to get ahead of myself a couple of weeks, when we get into things like the quasi-chemical model, the regular solution model has like a fundamental logical flaw. You're saying that the excess configurational entropy is 0, so it's randomly mixed, but then you have a heat that's not 0. Okay, well, let's suppose the delta H is negative. If the delta H is negative, it's because, remember that's epsilon AB, it's because this term is not 0. That is, the AB bonds are stronger than the AA and BB bonds. If delta H is negative, it's because the AB bonds are stronger than the AA and BB bonds, and so you will get then more AB pairs than the ideal. In an ideal solution, the number of AB pairs is 2XAXB. If epsilon AB is negative, it'll be bigger than that. And the number of AA bonds will be less than XA squared. Okay, you'll tend to have a shift of A's tending to, okay. So in that case, then the excess configuration entropy clearly is not zero. So there's this sort of logical flaw. You're saying SXS is non-zero, then you're saying delta H is non-zero. So what the system really tries to do is it does get a certain amount of order. If delta H is negative, then you will find that the number of AB bonds actually is greater than the ideal solution. If delta H is positive, then the number of AB bonds is less than the ideal number, and the number of AA and B bonds is greater. Okay, so if the delta H is negative, because the AB bonds are stronger, you tend to have ordering AB, AB, AB. If the delta H is positive, because the AB bonds are weaker, then you tend to have clustering. You tend to have A's clustering together and B's clustering together. If delta H is big enough, if positive enough, of course, it'll separate into two solutions. Now what the system tries to do then, as I said, is the system will find the distribution which minimizes G excess. SXS will be non-ideal, delta H will be non-ideal, and it'll find the balance that gives you the minimum G excess. Okay, and we'll do that in the quasi-chemical model. But I will tell you that in the quasi-chemical model, though, you can show that if the deviations from ideality are small, then it's still a reasonable assumption to assume that the TSXS term is less important than the delta H term. I'll show that mathematically later on. So this is not a bad assumption unless you get too far off, and then it starts to become a bad assumption. But even if SXS is not zero, the system is still pretty close to a random mixture. So you can show in the quasi-chemical model that as this omega minus A to T gets, this term gets bigger and bigger or smaller, whatever, deviates from zero, okay, that the A to T term at the beginning is much less important than the omega term. It's only later on that it starts to get bigger. Okay, so that's the general idea of a regular solution, which is I say it's the basis of most of the lattice solution models that we use. Okay, any questions about regular solution theory? All right, now I'm going to talk a little bit about phase diagrams. So, since that's what you're all dealing with, binary temperature composition phase diagrams. I'm going to go through these quickly. You should all know the theory of phase diagrams, but this is okay. So okay, I'm reading section 4.2, binary temperature composition phase diagrams. That's not the one I want. Okay, I'm sure you've all done this before, so let's go through it very quickly. Here's your germanium silicon phase diagram. You have the solid phase, you have the liquid phase, you have your two-phase region, melting points. If anybody wants me to go more slowly, let me know. Try to show how this is related to the Gibbs energy curves. So let's draw. Here we have the Gibbs energy curve for the solid phase. That's G of the solid phase. Here we have the Gibbs energy curve for the liquid phase. That's G of the liquid phase. Okay, the G of the solid phase goes from the chemical potential of pure germanium in the solid, mu naught germanium solid, over to the chemical potential of mu G naught silicon in the solid, and the liquid phase goes like this. This distance here is mu naught silicon liquid minus mu naught silicon solid. In other words, the Gibbs energy of fusion of silicon. And this distance here is the Gibbs energy of fusion of germanium. This is the Gibbs energy of mixing of the solid phase, and this is the Gibbs energy of mixing of the liquid phase. Everybody cool with that one? Okay. This is at 1500 degrees, which is up here, completely in the liquid range, where the pure liquids are more stable than the pure solids. Okay, so everywhere, including the two ends, the liquid phase is more stable than the solid phase, more negative Gibbs energy. Okay, so the liquid's always stable. If we went down to, okay, suppose we now lower the temperature. If we lower the temperature, several things change. The Gibbs energies of mixing will depend upon temperature. But to a first approximation, let's assume that the Gibbs energy of mixing don't change that much with temperature. What really changes is the Gibbs energies of fusion. So what really happens is, as you lower the temperature, the Gibbs energy of fusion is equal to the heat of fusion minus T times the entropy of fusion. The heat and the entropy of fusion are both positive. If you're at a high temperature, the entropy of fusion term, this term here, because of this term at high temperature, this predominates, and delta G of fusion is negative. Okay, so that's delta G of fusion, that's going from solid to liquid, so the liquid is more stable. But as you lower the temperature, yes, the heat and entropy of fusion change by the integral of Cp dt terms, delta Cp dt, but the most important thing is the T here. So as you lower the temperature, this term becomes less important, which tends to stabilize the solid. When you reach the melting point, the two terms are equal, and that's equal to 0, and below the melting point this becomes positive. So to a first approximation, what simply happens, you can imagine, as you lower the temperature, these two curves here move closer to each other and cross. You can think it's only the relative distance that matters, so you can think of one of them as constant. You can think of the liquid as constant and the solid curve moving down. As it moves down, it changes its form a little bit and so on, but the main point is it just moves down because these Gibbs energies of fusion at the ends become less and less and eventually become 0. When you reach the temperature of, if you reach exactly the temperature of 1414, which is the melting point of silica, then you'll find that this point has moved down to exactly this point. If you move now down to 1300 degrees, which is here, then the two curves cross of each other. This Gibbs energy now of fusion is positive, the Gibbs energy of fusion over here is negative, so pure silicon now at 1300, pure silicon is solid, pure germanium is liquid. The two curves cross, and I say that if you draw a common tangent, so this is a tangent to both curves, common tangent to both curves, which is a tangent to both curves at P1 and Q1, that P1 and Q1 are the liquidus and solidus compositions at that temperature. Okay, now you can look at this as two things. If two phases are in equilibrium, they must have the same chemical potential. Criterion for phase equilibria is equality of chemical potentials. Activities are equal. The chemical potential of silicon in the solid has to be equal to the chemical potential of silicon in the liquid, otherwise there would be a spontaneous transfer from one phase to the other. And of course, the tangent here, the tangent to the solid curve, if you project this tangent line, this straight tangent line up to pure silicon, the intersection point is the chemical potential of silicon at that point, but it's also the chemical potential of silicon at that point. So the common tangent assures that the chemical potential of silicon is the same in both phases. And if you project the line down to the other end, to the germanium axis, you get the equality of the chemical potentials. Okay, so you have chemical potential of silicon is the same in the two phases, the chemical potential of germanium is the same in the two phases. So that's your criterion for equilibrium. Now you say, okay, well the criterion for equilibrium is also minimizing the Gibbs energy. So the system wants to minimize the total Gibbs energy. Okay, so what you're going to have now is you're going to have two phases in equilibrium. You're going to have one point on this liquid curve in equilibrium with a point on the solid curve. Okay? And in between those 2 points, the system will follow the line. So I could imagine that I have, here's my liquid curve, here's my solid curve, and let me say, well, okay, this is the liquid curve, the solid curve. Let's say I have this composition of the solid in equilibrium with this composition of the liquid. So I have a phase here, and I have a phase here. In between those two phases, the mixture of the two phases will simply, the Gibbs energy will follow that line. Just by mixing it. If I have half of this and half this, I'll be halfway in between. Okay, but clearly that Gibbs energy, what point on the liquid line and what point on the solid line is going to give me the minimum Gibbs energy? Well, it's obviously the common tangent. This point here and this point here gives you the lowest possible common tangent. Any other point on the solid or any other point on the liquid, you're going to get a line that's a higher total Gibbs energy. Okay, so minimizing the total Gibbs energy or equating the chemical potentials is the same thing. Okay, it's the envelope. So over here you've got pure solid, you follow the envelope. Over here, over here you got pure liquid. So the actual system follows the one phase region here, moves along here, until it reaches here, and then goes up there. So you go through a one phase region, a two phase region. The one phase region, the common tangent is the lowest line joining 2 points, joining a point on one line to a point on the one curve to a point on the other curve. And it's also the line that gives you the same chemical potentials on the two phases. And as you vary, as you go down, as you start over here with 1300 degrees, you start with pure silicon, you move across, you have one solid phase, as the Gibbs energy of the solution follows this line. Then you have two solid and liquid phase, as the total Gibbs energy follows the straight line between Q and P. And then, as you continue on further, you now continue up the liquid curve here. And as you go from Q1 to P1, just by mass balance, the amounts of the phases change. At Q1, you have 100% solid and no liquid. Here you have 100% liquid and no solid. If you're exactly halfway in between, you have half one and half of the other. And that's the lever rule. Clearly then, as we move down to a lower temperature, the solid curve continues to go down through the liquid curve, and the common tangent line now at 1100 degrees, the common tangent line is moved over here. And eventually, when you get to 938, the two curves touch now at only 1 point, and below 938, now the solid curve is always lower than the liquid curve. Okay, so if you have reasonably convex looking Gibbs energy curves like this, the main effect is that as one descends through the other, the chemical potentials, it gives the Delagies of fusion change, and this then generates this lens-shaped phase diagram. So that's the basic thing. That's your primary effect. Secondary effect, of course, is the delta H also depends upon T, is delta Cp over T, and the delta S depends upon T, but not tremendously, and the delta Gs of mixing also are delta H minus T delta S, and they change too, but that's not the main effect. This is the main effect. Questions? All right, let's go back to 41 now. We've got a couple minutes. Okay, so everything I just said is said here. Okay, so the common tangent construction assures that the chemical potential is equal, so the chemical potential of germanium in the liquid is equal to the chemical potential of germanium in the solid on the solidus and liquid. Okay, and that's the criterion for phase equilibrium. Let's fiddle around a little bit with these equations. Let's take the Gibbs energy, take this equation here. Chemical potential of germanium on the liquid. This is equal to chemical potential of germanium on the solidus. This is when the two phases are in equilibrium. So this is when you write that out, you're talking about the equilibrium conditions. So what you mean is the mu excess liquid is the mu liquid is the Gibbs energy, the chemical potential on the liquid. So how does the diagram look? This is the solid and the liquid, then at whatever temperature. This point here is the mu excess on the liquid, and the mu excess on the solid means that the solid is point. Okay, and the two are equal. So when the liquid and solid are in equilibrium, the chemical potential of germanium on the liquidus equals the chemical potential of germanium on the solidus. Okay, so let's take that equation, this equation 122, and we'll subtract mu naught germanium liquid and mu naught germanium liquid from this side and from this side, and we'll add mu naught germanium solid to both sides. So this is just adding and subtracting mu naught of the pure material, mu naught the pure material on the both sides. Okay. Here I take minus mu naught germanium liquid from that side, minus mu naught germanium liquid here, plus mu naught solid, plus mu naught solid on this side. Okay, so mu minus mu naught is delta mu, or RT log activity. Okay, so this is delta mu of the liquid, or RT log activity of germanium in the liquid. This is delta mu of the solid, which is RT log activity of germanium in the solid, mu minus mu naught. This is the Gibbs energy of fusion of the pure material. So you have this equation here, which is another way. This is simply an equation expressing this equation, RT log activity of germanium on the liquidus, minus RT log activity of germanium on the solidus equals minus Gibbs energy of fusion, is basically just comes from this equation. Nothing new has been added. Okay, now, at some temperature, at this temperature here, which is not the melting point of germanium, delta G of fusion of germanium is not zero, obviously. It's positive, but no, it's negative at that point. Okay, so I thought that I said that when two phases are in equilibrium, they have the same activity. So, the activity of germanium in the liquid on the liquidus should be equal to the activity of germanium on the solidus. But, therefore, the left-hand side is zero. But it's not zero. So I've equated the chemical potentials, and somehow I've come up with the activities not being equal. How the hell did that happen? You see the problem. So the chemical potentials are equal. Except when two phases are in equilibrium, the chemical potentials are equal. When two phases are in equilibrium, the activities are equal. But it seems that the chemical potentials are equal, but the activities aren't equal. Standard state. This is RT log, this mu liquid minus mu naught germanium liquid is the activity of germanium in the liquid state relative to the liquid standard state. And activity is always a relative quantity. It's mu minus mu naught. RT log activity is mu minus mu naught. You're always referring the activity to a standard state where the activity is 1. So this is the activity of germanium in the liquid, which means that the activity of germanium in pure liquid would be 1. This is the activity of the solid, germanium, in the solid relative to the solid standard state. The solid standard states aren't the same. Two activities, if two phases are in equilibrium, they have if two phases are in equilibrium, a component will have the same activity in both phases, provided it's with respect to the same standard state. If it's not with respect to the same standard state, then you have to have a standard state change, which is what this is. This is simply the difference. Here the standard state is mu naught liquid, this is mu naught solid, this is the difference in the standard states. Okay, so be careful when you say activities are equal to 1. And I've had people, well, say the same thing if you take say you take a eutectic diagram. Here you have liquid, here you have liquid plus A, solid, or B, sorry, B, solid. And here you're on the thing, so you say, well, at this point on the liquidus, the activity of the liquid is the activity of B is 1, because it's in equilibrium with pure solid, so the activity of B on the liquidus must be 1. Well, no, the activity of B on the liquidus is equal to 1 with respect to the solid standard state, but is not equal to 1 with respect to the liquid standard state. All right, and then if you start with the other equation, how did I do that? No, you touch a button and it goes crazy. Then if we start with the other equation, the equality of the chemical potentials of silicon, then we clearly end up with an identical equation for silicon. So those two equations here, this is another way of looking at it. You could use this equation and this equation. They will also allow you to calculate the solidus and the liquidus. We'll do that. Come back to that a little bit later. But I went through it here. Let's talk a little bit about the standard states. Notice the relative positions of the chemical potentials are completely arbitrary. The mu naught liquid and mu naught liquid is arbitrary. This is immaterial for the preceding discussion, so you can take take the curves here. It doesn't matter how the relative value. I could take both these points here, raise this point by 1,000,000 joules, make this point by 1,000,000 joules. It would not change the position of the points of tangency. Okay, you're just making a linear shift of the curves. Okay. As long as you keep the distances between them the same, the endpoints don't really matter. They're completely arbitrary. At least one is. This point, one point over here, one endpoint over here, and one endpoint over here are arbitrary. The rest are not arbitrary. So you can move the whole thing up by any amount you want or down. You'll get the same tangency points. It won't change the compositions. All right, let's take 10 minutes and go for another 10 minutes afterwards. Just want to finish up a couple of things. You have to turn it on. All right, if we can do this in 10 minutes, then we can finish up. There's a couple of things I wanted to finish up. So we're here on page 42. Okay, so the two-phase lens on the phase diagram, the solid-liquid region, is determined that two curves move relative to each other as the Gibbs energy of fusion varies with delta H minus T delta S. It's interesting how so the temperature dependence of this Gibbs energy of fusion is the delta S naught fusion, and it's rather interesting to see how the shape of the phase diagram the shape of this two-phase region is influenced by varying the Gibbs energy of fusion. So I took a phase diagram in figure 14 in which I have a system AB in which the liquid and solid are ideal Rayoltian solutions. So the liquid and solid are Rayoltian. I let the melting points be 800 and 1200 K. Okay, and I assume that the entropy of fusion was either 3, 10, or 30 joules per mole. So that's the only difference in these diagrams. So let's go to figure 14. So there's figure 14. These are hypothetical phase diagrams for a system AB. And in the diagram, I assumed the liquid and solid were both ideal mixtures, so the delta G mixing is just the ideal term. In all three diagrams, this melting point is 800 degrees and this melting point is 1200 degrees. I'm assuming that the heat and entropy are constant, but I'm letting delta S naught fusion. For example, here it's equal to 30. Okay, so if it's equal to 30, and if the melting point is 1200, then the heat of fusion at the melting point, the melting point of B is equal to 1200 K. So at the melting point, the Gibbs energy of fusion is 0, and that's equal to the heat of fusion minus 1200 times, in the top panel, 30, and so the heat of fusion of B then is equal to 30 times 1200 and so on. Okay, so I assume three different entropies of fusion. Okay, and I change the heat of fusion according to these so that just the temperatures of fusion stay the same. Clear what I've done then? Over here, the heat of fusion. So this 10 joules per mole, the heat of fusion over here is 12,000, the heat of fusion here is 8,000. Here it's 3,600 and here's 2,400. Okay, so that's the only difference. The liquid and solid are still both ideal solutions. All that's changed is the entropy and the enthalpy of fusion have both been decreased by factor. And you see the effect it has in the phase diagram. And you can sort of think about that at home. Think about those two curves coming through each other. The shape of the curves is the same. The Gibbs energy of mixing, which is the distance there, stays the same. It's just that the rate at which they're moving through each other is different. And it ends up this way. So this is rather interesting. What it means then is the entropy of fusion becomes smaller, the lens becomes narrower. So this is rather a typical 10 joules per mole is sort of a typical entropy of fusion of a metal. And so this is sort of a standard width that you might expect for a two-phase region between a solid and liquid metal. Now if you take something like a salt, like sodium chloride, its entropy of fusion is per mole is generally twice as much as a metal, mainly because you've got sodium and chlorine. You really have 2 moles of atoms. Okay, so you got a bigger entropy, and that's why when you look at salts and things, you tend to have fatter looking two-phase regions. Now, if here this is solid liquid, but I mean, you can say your phase diagram, rather than solid liquid, this was liquid gas. It's exactly the same thing, but now instead of the heat of Gibbs energy of fusion, you got the Gibbs energy of vaporization. Okay, so just do exactly what we did before on figure 13, but instead of solid and liquid, just read liquid and gas. Instead of fusion, read vaporization. But now the entropy of vaporization is about 10 times the entropy of fusion for most materials, because there's a much bigger change in disorder. And that's why when you look at a phase diagram between a liquid and a vapor, you see a much fatter two-phase region than you do for a typical solid-liquid region. Now, supposing you're changing, you'll see 2 regions like this between 2 solid allotropes. So this is the body-centered and this is the face-centered. Okay, and then you tend to find between 2 allotropes, 2 different solid-state structures, you have extremely narrow two-phase regions. And that's because now we're going from alpha to beta, and this is delta G of the alpha-beta transformation. And the entropy of solid-state transformations tends to be about 10 times less than that of the solid-liquid, because the entropy change is so much smaller, not much change in disorder as you go from one structure to another. So solid-liquid phase diagrams tend to be very narrow two-phase regions, liquid-solid wider, liquid-gas wider. If you have a really big number of atoms per mole, it also tends to be wider. That's the fundamental reason that. So you see that. Something else I'm not going to talk about, the effect of grain size. The foregoing phase diagram calculations assume the grain size of the solid phases is sufficiently large so that the interfacial energy between the solid and the liquid is a negligible effect. You're assuming like this is a big solid, big chunk of solid, small liquid. It's also been assumed that strain energy is negligible. For very fine grain sizes in the submicron range, the interfacial energy can be appreciable and will have an influence on the phase diagram. So when you have a solid and liquid phase in equilibrium, you have to take into account the interfacial energy as well, if you have very small grain sizes. And this can actually affect the liquidus temperature. And this effect could be important with the development of materials with grain sizes in the nanometer range. And interfacial and strain energies also increase the Gibbs energy of a phase, because you're introducing vacancies, dislocations, all sorts of things. And this will decrease the thermodynamic stability. So as you strain a phase, the solid tends to make it less stable, which will then lower the liquidus temperature somewhat. In particular, the liquidus temperature of a fine grain solid will be lowered, not just because of the interfacial energy, but because of the grain energy between. Up here I was talking about the first paragraph, I was talking about the liquid-solid interfacial energy. Now I'm talking about within the solid phase itself, the fine grains. You know, grain boundary energy within the solid phase, and this is always positive, and that will then tend to destabilize the phase. So very fine grain solid will have a lower liquidus. If a suitable estimate can be made for the grain boundary and strain energies, then this could simply add this to the Gibbs energy expression for the phase, and you could then calculate the phase diagram. Let's take G solid and add on the strain energy and then on the interfacial. That was a temperature the diagram what it did was temperature composition, assuming that pressure was constant. You can also flip things around and do a pressure composition diagram, assuming temperature is constant. Here we have the diagram. This is pressure. I plotted it as log pressure, so it looks a bit nicer. versus composition for the zinc magnesium system at constant temperature. So this is a PX diagram at constant T. Again, you see you got a kind of a fatter solidus liquid vapor region. So this is high pressure. High pressure stabilizes the liquid, low pressure stabilizes the vapor phase. It's going to be the same thing. You're going to have two curves. You're going to have a curve for the vapor phase, you're going to have a curve for the liquid phase, and you're going to have a common tangent line between them, and the points of common tangency dictate the compositions of the phases at equilibrium. Okay, and once again, this is the whole thing, and this is the Gibbs energy of the magnesium vapor. This is the Gibbs energy of magnesium liquid, and the same thing for zinc over here. So what we have to do now is, when we were doing this with terms of temperature, when we had temperature versus at pressure constant, we had to find an expression for this difference in terms of temperature, and this is what we came up with. It's H minus T delta S. So that shows you how those endpoints vary with temperature when pressure is constant. Now if we're trying to calculate this diagram, we have to come up with how the difference between the chemical potential of the vapor and the liquid varies with pressure. So how the Gibbs energy of vaporization changes with pressure. Right? And the expression we use is this one here. The Gibbs energy of vaporization is the standard Gibbs energy of vaporization. In other words, the Gibbs energy of vaporization going to a vapor in 1 atmosphere plus RT log P. We've already derived that. Go back and think about it. But that equation there, 128, is sort of equivalent to this. This gives you the Gibbs energy as a function of pressure. This gives you the Gibbs energy of phase transition as a function of pressure when the temperature is constant. This gives you the Gibbs energy of phase transition as a function of temperature when the pressure is constant. So this equation here then allows you to change pressure and bring those 2 points together. So as you increase the pressure, you stabilize the liquid phase. So as you increase the pressure, these two phases move down. This vapor phase moves down relative to the liquid, or the liquid moves up relative to the vapor. Same thing, the two curves pass through each other, and you got the expression. So actually I did that calculation. That is actually a calculated diagram. I actually put the numbers in here and calculated that diagram, so you can read that and you'll see exactly how they solid liquid, I won't bother to go through that. Let's do one last little thing and then I'll stop. We talked about phase diagrams with complete solid and liquid miscibility, like the germanium silicon system. Sometimes you see minima and maximum in a two-phase region. So I want to explain that, then I'll quit. Now here's a typical phase diagram. I've done this for a hypothetical system. Why did I do that? Because it was easier to draw. Okay, here's an actual system here. This is the potassium carbonate, sodium carbonate phase diagram. It's a two-phase region. You have complete liquid miscibility, complete solid miscibility, but rather than having a lens-shaped two-phase region, you actually have a minimum in it with liquid and solid regions on the two sides. Okay? So how do we explain that? Let's consider the composition. Let's consider a temperature. Let's consider this temperature here, the temperature where I've drawn these two common tangent lines. So at this temperature here, over on this side, you have pure solid, then you have two phases, then you have pure liquid, then you have two phases, then you have pure solid again. So at that temperature, or whatever, about 725 degrees, when you rotate this, you rotate the whole thing, don't you? Right. Now the other one's upside down. Okay, this is the Gibbs energy. This would be the Gibbs energy composition curve at that temperature of 700 degrees. And what you see is you have the solid, the liquid curve goes like this, between the pure liquid phase over here and the pure liquid phase over here. And the solid goes between the pure chemical potential of the pure solid over here and the chemical potential of the pure solid. So what you see is that for pure A, the solid's more stable than the liquid. For pure B, the solid is more stable than the liquid, but somewhere in the middle, the liquid is more stable than the solid. Because the curve, liquid curve is drops down further than the solid curve. This is due to the excess properties. Okay, so it's totally wrong. Due to the excess properties, you simply have your liquid curve. This is delta G liquid, is delta G ideal plus G excess of the liquid. And for the solid curve, you have a curve like this, where delta G of the solid equals delta G ideal plus G excess solid. So clearly G excess solid is greater than G excess liquid, more positive or less negative or whatever. Okay, but it's the relative. So the liquid curve goes down more steeply, it's more stable relative to the ideal. This is negative here, in this case. In this case you consider this to be positive, which makes the phase less stable. Okay, so the fact of mixing destabilizes the solid relative to the liquid. So when the phases, there will be then a temperature when the phases intersect, that they will intersect as they do here. The solid curve is flatter than the liquid curve. Okay, which means the solid is destabilized relative to the liquid because of the mixing. Okay, so now clearly there will be a point where there will be some temperature. Some temperature then when the two phases cross, as they do here. And now there will be two common tangents. There will be a common tangent on this side and a common tangent on this side. Hence you will have two phase regions. As shown in the next slide, which is now probably upside down. Okay, but there's your two phase regions. Now, as you lower the temperature, say we start, so that was 700 degrees. That was this temperature here. So now as we lower the temperature, the solid phase continues to descend. And now your two common tangent lines, which are like this, move along like this until P1 and P2 touch. Okay, and that then when P1 and P2, when this goes down to a low enough temperature that P1 and P2 touch, then what you have is basically your liquid curve is like this, and your solid curve now touches at just one last point. That's the minimum point. You go to lower temperatures, the solid phase comes right off. Okay, so your common tangents move like this and then disappears. So when P1 and P2 become coincident, that's the lowest temperature. That's the must be some way of just rotating one of them there. Okay, that's the minimum temperature there. That is not a eutectic. If you cool the liquid down, it will melt isothermally like a pure material. Okay, so it's a quasi one-component system, if you like, but it's not a eutectic. A eutectic is liquid gives two solids. This liquid gives a solid at the same composition. It's just a point where things are right in balance. It's not a eutectic. It's not an invariant. It's not an invariant. It's a quasi one-dimensional, one-component system, if you like. It's different from an invariant reaction in terms of the phase rule. Now that occurs then because G excess solid is greater than G excess liquid. That gives you a flatter G excess solid curve and results in this. This of course means that the solid is less stable than the liquid, both relative to ideal solutions. So you've stabilized the liquid relative to the solid. So it's like you have the two-phase region in the germanium silicon system and you push it down in the middle. You're taking this two-phase region and you're pushing it down, stabilizing the liquid. If you push it down enough, the thing will come together and you'll end up with a minimum. Now that could be because the solid has positive deviations or because the liquid has strong negative deviations. It's usually the former. If you have deviations in a solid phase, deviations in the liquid phase, the deviations in the solid phase would generally tend to be of the same sign, but more. So I mean, if the liquid has slightly positive deviations, the solid's going to have even more, simply because it's harder to pack things in together. If the liquid doesn't want to mix, GXS is positive, means the A's and B's have a tendency not to want to go together. By the regular solution theory, A and B bonds are weak. In the liquid, they can sort of accommodate themselves around, but in the solid, it's harder to fit everything in. Okay, so if the solid has positive deviations, the liquid tends to have less positive deviations. So there you have so that's why you generally get a minimum, because this phase has been destabilized relative to this phase through the excess properties. Okay, the greater the difference, the lower the minimum. As this difference becomes greater, the minimum is pushed down even further. In principle, we could have a maximum in a two-phase region of a diagram with complete miscibility. So you could have a phase diagram versus temperature in which you saw a diagram like this. No intermediate phase, complete solid miscibility, complete liquid miscibility with a maximum. Thermodynamically, that's completely possible. All you have to do is the GXS of liquid would be greater than GXS solid. But this is very unlikely, because if GXS in the liquid was positive, that means the liquid doesn't like to mix, then the solid is going to like to mix even less. So this means the liquid, somehow the solid is stabilized, but is okay, but the liquid doesn't want to mix, and that isn't going to be the case if you just have simple, like regular solution. So I have never actually ever seen a diagram that looked just like that between a solid and a liquid. Now, you do find maximum in two-phase regions all the time in phase diagrams, and that would mean that the solid is very stable relative to the liquid. And when do you see a maximum in a two-phase region in a simple binary solid-liquid, a simple binary phase diagram? When I say you never see a maximum, I mean you never see a maximum above complete solid solubility. Okay, but you see all the time a diagram that looks like this. Say A and B, that's the phase diagram. So here I have liquid, here I have a compound AB, non-stoichiometric compound. So here you've got liquid plus AB, and over here you've got liquid plus AB, and this is clearly a maximum in a two-phase region, just like this. But it's above an intermediary phase, AB. It's not above the entire. So this definitely means now that the solid is stabilized relative to the liquid. This has made the solid more stable. It's made the solid more stable, though, because the solid has become ordered. It's formed an AB solution with very strong AB bonds, which has stabilized it enthalpically relative to the liquid, which is more randomly mixed. But this, the maximum here, and this minimum here, thermodynamically, they describe the same thing, intersection of the Gibbs energy curves. If I were to take this diagram and go across at this temperature here, okay, if I went across at that temperature, and at that temperature I draw the Gibbs energy composition curve at that temperature, I would find the liquid phase that went like this, and the solid phase went like that. Okay, so the liquid phase is more or less normal. The solid phase is strongly stabilized around that composition where you have AB, AB, AB. But as you get away from that composition, its Gibbs energy goes up. It's stabilized because you have A's next to B's. If you start to get away from that composition, it goes up. Now you have two common tangents, which give you the okay, that's enough for today. A lot of stuff to do on the weekend for you. Six is using the activities in chemical reaction equilibrium constants. So 9, 1, 3, 4, 6, 7, 8, 11, that's equilibrium constants with activities. 7 is the Gibbs-Helmholtz equation. Number 1, 3, and number 11 is playing around with some of the partial properties equations 1, 3, 4, 5, 6, and 11. And for reading, what section was I at here? Okay.
5-3, 5-4, 5-5-1, 5-6, 5-7.